Hey team, welcome to the numbers game. I'm Coach T, and in this tutorial we're going to be proving continuity of a function. Now before we get started, make sure to subscribe to the channel for notifications on more math tutorials. Alright, now let's take a look at this example. In this example, we're given the piecewise function f of x equals x squared if x is rational, and f of x equals 3x if x is irrational, and we're being asked to prove that f is continuous at x equals 0 and x equals 3, and f is discontinuous at x does not equal 0 and x does not equal 3. Now in this tutorial, we'll be proving that f is continuous at x equals 3. I've proven that f is continuous at x equals 0 and f is discontinuous at x does not equal 0 and x does not equal 3 in separate tutorials, and I'll include the links to those tutorials in the description box. We'll start by doing our scratch work, and let's start with the case that x is rational. We've got the absolute value of f of x minus f of c. C in this case equals 3, so that's the absolute value of f of x minus f of 3. When x is rational, f of x equals x squared. And when we plug x equals 3 into x squared, we end up with 9. So this simplifies down to the absolute value of x squared minus 9. Okay, so I want to take a moment here to evaluate what we're looking at. Now the goal is to show that the absolute value of f of x minus f of c is less than epsilon. That means for us, we're trying to show that the absolute value of x squared minus 9 is less than epsilon. So here, I want you all to take note of the fact that it's going to be kind of hard to keep the absolute value of x squared minus 9 less than epsilon, especially given that epsilon can be, and typically is, an arbitrarily small number, and x squared minus 9 has the potential to be a really big number because x is being squared, right? So we need to put a constraint on x, or rather the range of x, to ensure that the absolute value of x squared minus 9 doesn't get too big and completely blow up our proof. So let's take a deeper look. I'll factor x squared minus 9 so that we get the absolute value of x plus 3 times x minus 3. And then I'm going to split the absolute value. So the absolute value of x plus 3 times the absolute value of x minus 3. So we see here that x minus 3 is not really the factor that's going to cause us trouble. It's really the x plus 3 piece that's problematic. So we're going to focus our attention on controlling the absolute value of x plus 3. So at this point, I'm going to set this less than epsilon. So now at this point, the goal is to control the absolute value of x plus 3 so that this can actually remain true. Let's start by constraining the absolute value of x minus 3 to be less than 1. If the absolute value of x minus 3 is less than 1, then the absolute value of x plus 3 can be rewritten as the absolute value of x minus 3 plus 6. And then I'll move the plus 6 to the outside of the absolute value. So that's the absolute value of x minus 3 plus 6. And if the absolute value of x minus 3 is less than 1, then this piece here will always be less than 7. So essentially, I'm saying that the absolute value of x minus 3 is a fraction or a decimal, given that it's between 0 and 1. And as long as the absolute value of x minus 3 is a fraction, when we add 6, we'll always be approaching 7, but not quite reaching 7. So now that we've bounded the range of x, we can say that if the absolute value of x plus 3 times the absolute value of x minus 3 is less than epsilon, then two things need to happen. The absolute value of x minus 3 has to be less than 1, and then 7 times the absolute value of x minus 3 will be less than epsilon. So what we did was we replaced the absolute value of x plus 3 with 7. Now if this is the case, then the absolute value of x minus 3 is less than 1, and then the absolute value of x minus 3 is less than epsilon over 7. And this is what we're going to set our delta as. All right, so that was just the scratch work for the case that x is rational. Now we'll move on to doing the scratch work for the case that x is irrational. So we'll start off, of course, with the absolute value of f of x minus f of c. C equals 3, so we've got the absolute value of f of x minus f of 3. When x is irrational, f of x equals 3x. And when we plug in x equals 3 for 3x, we get 3 times 3, which equals 9. So this simplifies down to the absolute value of 3x minus 9. I'll factor 3 to the outside of the absolute value, so that's 3 times the absolute value of x minus 3. And that's all the simplification that needs to happen here, so this will be less than epsilon. Now, if 3 times the absolute value of x minus 3 is less than epsilon, then the absolute value of x minus 3 is less than epsilon over 3. And we did this by dividing both sides by 3. And epsilon over 3 is what I'll set delta equal to. So we'll combine the deltas that we found in each of our cases to get delta equals the minimum of epsilon over 7, 1 epsilon over 3. And now that we've finally identified our delta, we can start our formal proof. Of course, we'll let all epsilon be greater than 0. And then we'll let delta equal what we found in the scratch work. That is, we'll let delta equal the minimum of epsilon over 7, 1, and epsilon over 3. Then for the absolute value of x minus 3 less than delta, we have, for case 1, when x is rational, the absolute value of f of x minus f of 3, which simplifies to the absolute value of x squared minus 9, which equals the absolute value of x plus 3 times x minus 3, which equals the absolute value of x plus 3 times the absolute value of x minus 3. And this is less than delta, which we said is equal to epsilon over 7, and epsilon over 7 is less than epsilon. So we've shown that the absolute value of f of x minus 3 is less than epsilon for when x is rational. Next, we'll move on to case 2. We've got the absolute value of f of x minus f of 3. This equals the absolute value of 3x minus 9. Factoring out 3, we have 3 times the absolute value of x minus 3. And this is less than delta, which equals epsilon over 3. And epsilon over 3 is less than epsilon. So therefore, we've shown that f is continuous at x equals 3. And there you have it. We've proven that our function is continuous at x equals 3. If this video was helpful for you, give it a thumbs up, like the video, and subscribe to the channel for notifications on more math tutorials. I'm Coach T, and thanks for watching The Numbers Game.